All right, guys. So what we're going to be doing in this lecture is advanced integration by parts. Um, it's not that bad, but it is a continuation of what we did last time. And so these are kind of trickier problems. So we're just trying to separate out the tricks into one lecture rather than teach you the basic ones and the tricks all in the same lecture. So we're going to get right into it, and we're going to learn a few different tricks, basically. So there's not really any theoretical motivation for this. They're just tricks. So let's see here. Mostly just algebra tricks and things like that. But you do need to know your basic integration by parts. So recall integration by parts. The formula. So the formula says the integral of u dv equals uv minus the integral v du. Okay, so that's our basic thing. Also, we didn't do it last time, but it should come up today, is that if you have an integral that's a definite integral like that, the easiest way to work it out is to just say, well, let's do the same thing. And then just when you're done, like you work out the entire integral, and then you just plug in your a and b. You'll see it other ways. You'll see it this way. uv evaluated from a to b minus the integral from a to b v du. But it just becomes a lot of trouble, in my opinion, to write like the a's and b's in multiple places like this. And so from my point of view, just do integration by parts like normal all the way to the end, and then just plug in your limits. So basically there's nothing special for a definite integral. We'll probably see those pretty soon, but not right away in this lecture. Okay, so let's see our first trick. So first trick. So what is the trick? It's using a substitution before integration by parts. And also, a lot of people abbreviate integration by parts, IBP, integration by parts. So here's an example, and we'll see how it works. I mean, it is exactly what it says, but this will show you a good time to do it. All right. Now, if you tried to do this just with regular integration by parts, you will not succeed. Okay, you won't. So we do need some kind of trick. And it looks complicated anyway, so you might realize that it needs some kind of trick. And basically, here's the idea. If you take whatever's in the exponential and you do a u substitution. Now, I'm not actually going to do a u substitution because we're going to do integration by parts. And when we do integration by parts, we have u's and v's. So if I'm doing a substitution here, something that's smart to do is do a different letter than u. Okay, so I'm going to do like, well, what's another letter? Z. I'm going to do a z substitution. So let z equal x to the 8, right? Inside function. That's what we want to be our u, usually. So you have that. So that will tell you that dz is, we're going to take the derivative, 8x to the 7th dx. Okay, let's just divide that 8 over to the other side now. Have dz over 8 equals x to the 7th dx. Okay, now look at what we've got here. You probably didn't notice because there's not a reason to, but in your dz, you have an x to the 7th, right? And in your z, you have an x to the 8th. And magically, the x to the 8th and the x to the 7th, if you combined them, 8 and 7 turn into a 15. And that is what is going to let us do this trick. Okay? Because you can take this integral and just rewrite it this way. So I've got a 14, and then instead of x to the 15, I'm going to write it as, well, it's an x to the 8 and it's an x to the 7, right? Multiply them together, and you get e to the x to the 8. So just moving a couple things around like that. Okay, so I'm just rearranging things, just rearranging them. Now, now that I've rearranged them, though, what I can do is I can say, well, I've got an x to the 7th dx, just like this x to the 7th dx. So that's great. That's going to give me a dz over 8, right? And then I've got an x to the 8th. That's not what I wanted to do. I have an x to the 8 in 2 places. So those are z's. So substitute it in, and we will get 14 x to the 8th, which is z, and then e to the x to the 8, which is e to the z. So move your constants out front. We got 14 over 8 integral z e to the z dz. So let's move it over here. So 14 over 8 is 7 over 4 when you simplify that, and then integral z e to the z dz. Now this is a basic integration by parts formula now, right? Because if you're going to do just regular basic integration by parts, we're just going to pick u to be z, dv to be e to the z dz. Remember, everything has to be u or dv. So in this case, the z is the u, and then that means that everything else has to be your dv. Okay, so back to work. So from u to du, remember what to do. You take a derivative. So du is dz, and here to dv to v, you antiderivative. And so the antiderivative of e to the z is e to the z. Now, then you go to your formula, right? So your formula for integration by parts says we should be getting uv minus the integral v du. Just writing that big because take up space. So what is that for us? So uv, that's going to be these two on the diagonal here. So uv is z e to the z minus integral v du. V and du are these two. So multiply them together, you just have e to the z dz, which now you can integrate. Now, also, something I forgot here. We had a 7 over 4 out front, so I should have a 7 over 4 outside everything. So I should have a 7 over 4 outside everything. So I should have, whoa, what happened? So I should have a 7 over 4 outside everything. Right, so 7 over 4, z, e to the z, minus, you have another antiderivative of e to the z, which is e to the z. And actually, we can move parentheses over. Okay, so that's what we get. Now we're not quite done because remember, z was our substitution variable. Back up here at the top, z was actually x to the 8th. So you go back and you substitute in x to the 8th. So we're going to get 7 over 4, x to the 8, e to the x to the 8, minus e to the x to the 8, plus c. And we're done. So that's that. Now, the point, right? The point is that you would not have been able to do it without that special algebra that we did. And it wasn't, fancy algebra, but you just had to know, You had to know that you just basically had to recognize that if you made this substitution here, that it would just magically work out because the x to the 8th and the x to the 7th somehow added up to that 15 up there. Okay, so that's how that works. That was highlighted, right? I don't know. Okay, anyway. So that's one thing you can do. And you should be able to recognize those in the problem set. They all look basically the same. Oops. All right. So there are others that are like this. So here's another one, just same kind of idea. So, all right, so here we go. So what you can do is basically, is this gonna work? I think this is gonna work. The cosine and the natural log are not multiplied here, right? The natural log is inside the cosine. So you can't pick cosine to be u and natural log to be dv or something like that. Like these have to stay together because the natural log is inside of the cosine. So it looks like there's not a lot of choices here. Basically, what you're going to have to do is you're going to have to pick the u to be the cosine ln x, because we don't really have a choice, and the dv could just be whatever else is left, which I guess in this case is negative 11 dx. Probably does not matter where you put that 11. Like it could have been over here. Doesn't really matter. All right. So you pick that because you don't really have a choice. So remember what to do. Derivative over here. Now this is a more complicated derivative than we normally have, but it is what we have. So you take the derivative, and you can get the derivative of cosine is negative sine. So you get negative sine ln x times the derivative of ln x, which is 1 over x. Then here, remember, you do an antiderivative. So the antiderivative of 11 dx is 11x. So this is what you get. Now you don't know if you've really made an improvement. You have to just work it out. So remember how this goes. We're going to be going uv, right? Let's write it uv minus integral v du. So what's uv? It's the two that I highlighted. So it's cosine ln x times negative 11x minus the integral v du, which are these two. So v du is negative 11x times negative sine ln x times 1 over x dx. Okay, so what happens here is that the x and the x can cancel, and what you're going to get is, we'll see, negative 11x cosine ln x. We have a minus, that'll be a plus, integral of, what do we have? The 11, oh actually, no, right? There's a minus, so that's a minus. We canceled the x's, so we have 11, and then just sine ln x. dx. Okay, now here's the thing, is that this didn't really get us anywhere, right? Like we started with a cosine ln x and we didn't know how to do it. And now we have a sine ln x and we don't know how to do it. And so what you do is you do integration by parts again. And so I apologize, but this this problem here is actually too hard. The technique is one that I wanted to show you, but I wanted to show you an easy one before a hard one, and I didn't realize that the homework was just giving me a hard one right away. So here's what you have to do. This integral needs integration by parts again. Okay? Use integration by parts again. So you have to do that whole process again. So we go, it's the exact same process. U is sine ln x. We're basically making the same choices we already did. U is sine ln x. The dv could just be dx because I took that 11 out. Du, you're going to go cosine ln x, 1 over x dx. Everything's basically the same. V, take the antiderivative of dx and get x. And what we're going to get now is, so we're writing this all out, negative 11x cosine ln x minus 11. And then here in brackets, we have to do our integration by parts again. So we need uv. So uv is x sine ln x minus the integral v du, which are the two on the bottom, these two. So we're going to have cosine ln x, 1 over x times x, and then a dx. Now, just like last time, the x's go away, and let me write out the full thing of what we have now. Okay, so you need the original integral. So the original integral is up here. So the original integral was negative 11 integral cosine ln x dx equals, and I need to write out all this junk. So we've got negative 11x cosine ln x. I'm going to distribute this 11 through both of these. So negative 11x cosine x, and then 11 minus 11x sine ln x. And then the third term is going to be a minus 11 times a minus, which will be a plus 11 integral cosine ln x dx. Now, look at what we've just accomplished. We're a bunch of freaking geniuses over here. We started with the integral of cosine ln x dx, and we did this much work, and we turned it into the integral of cosine ln x. So all of that work just gave us back the same integral that we started with. And so you feel like you didn't do anything useful, right? But you did, because if you're very sneaky, we just did something very clever. Okay, so what we did was we integration by parts twice. We magically ended up with the same integral. Now, if you write it all out as an equation like we did, we have the same integral on both sides of the equation. Now, you still don't know how to do the integral, right? But guess what? You don't need to know how to do the integral, because you can solve for it with algebra. And that's what this technique is. Solve for it with algebra. Very strange technique, okay, but that's what we're going to do. So how do you even do that? Well, I guess first of all, I did not leave myself enough room to do it, so I'm going to move all this text. So let me move this down just a little bit. Okay, how are we going to solve for it with algebra? Well, here's what we're going to do. On the right-hand side, I have plus 11 integral cosine ln x. Well, what if I subtract 11 integral cosine ln x? If I subtract it on the right, I subtract it on the left. Now let's see what we get when we do this. So equals. On the right, I'm going to write out the right-hand half. We have a negative 11x cosine ln x minus 11x sine ln x. Now over here on the right, they just canceled. But on the left, they don't cancel because it's negative 11 minus negative 11. Add them up, you get negative 22 integral cosine ln x dx. See, now instead of having the integral in two places, we actually only have the integral in one place. So now all we have to do to solve for the integral is just divide both sides by 22. So you just go over 22, I guess negative 22 over negative 22, and we get integral cosine ln x dx equals, divide everything by negative 22 over here, and it's just going to be 1/2 x cosine ln x, looks like plus another 1/2 x sine ln x. And don't forget to add a plus c. I mean, in the homework, you know, they never make you, but on this one you do. All right, so let me just say one more thing about this. I'm looking at the answer that we have, and according to the answer, I was supposed to have a 2 here and not a 22 here. And so somehow I made a mistake. Let me figure this out. I took the 11 out, so I didn't have an 11 there. Then I multiplied by the 11, so 11. Okay. Oh, okay. Okay. So this is correct, but this is actually not the integral that they asked for, right? I screwed up because the one that they asked for was supposed to have an 11 right here. And I lost my 11. So what I should have done, if I go back here, is not divide everything by 22, because I'm supposed to have, I want to have an 11 there when I'm done. So I should just divide by negative 2 or 2. Where is it? I want a negative 11, so I should have divided by 2. In which case, I'm going to end up with the negative 11 there, and then this will be negative 11 over 2 and negative 11 over 2. All right. So I solved for the integral without the 11, but I was supposed to have the 11 there. Okay, so that's something. Now, I'm going to show you an easier one right now. Okay, so if none of this made sense, then watch the integral that I'm about to do, and then go back and look at the one that I just did. Okay, because like I said, we did this out of order because the homework upset me by making me do a hard one first. Okay, so here's an easier version of the same type of thing. So let's say find integral e to the x. Yeah, that's fine. Sine 2x. It's more interesting with those numbers like 2 there, so that's why I did that. I thought about changing it to e to the 3x, but I didn't. So this is what we have. All right. So when you see this kind of thing in particular, sine and e to the x or cosine and e to the x or that kind of thing, it's really a clue that you're going to have to do this solve for the integral with algebra thing, okay? So it should look like that to you. You should recognize it. Solve for integral with algebra, okay? But this is an easier version. And so this version you can actually do with integration by parts twice, but you can use tabular integration. So I'm going to say use tabular integration by parts to make it easier. All right, so we have to remember how to do that. So here's how you do that. So you make a table, UDV. Now, you can pick using the LIATE thing for priority, but it doesn't matter here, so just pick whichever. I'll pick the sine 2x to actually be the u, just because with the 2 there, it'll be easier to take derivatives than antiderivatives of the sine. Once I pick that that's the u, then du must be e to the x. Okay, now when we did this in the notes, I took derivatives here until I got to 0. Well, you're not going to take derivatives until you get to 0 this time. You're only going to do it twice. So only do 2 derivatives. Why 2? Because that's what makes it work, okay? So take the derivative of sine 2x. It is 2 cosine 2x, right? The 2 is from the chain rule. It's cosine 2x times 2. Take one more derivative. So you're going to get negative 4 sine 2x. Stop. That's as far as we want to go. Now for the other one, we're going to be doing antiderivatives. Now the antiderivative of e to the x is very easy. It's just e to the x and e to the x again. Okay, so now we've got the table for tabular integration, and it's set up for, we did it twice. Okay, so remember how this works. So I'm gonna make this big. The way this works is you put a line here, a plus, and a line and a minus, and a line and a plus. Okay, and then you multiply all the stuff that I drew the lines between. So what I get is that the original integral, here it is equal to the first 2 multiplied, so these 2 with a plus, so I'm going to get plus e to the x sine 2x. Then these 2 with a minus, so minus, multiply them together, looks like 2 e to the x cosine 2x. And remember, the one that was horizontal is special. That's the integral. So I'm going to get a plus, because that's the sine, integral, and then I multiply these 2 together on the bottom. So what do we have? Negative 4 sine 2x e to the x. Okay, didn't really leave myself enough room. All right, now what happened though here is that the same thing in the previous problem. This integral is the same as this integral. And that's why we did this twice, was because 2 times will make that happen. Okay, so if we're going to solve for it with algebra, we're going to take this and add 4 integral sine 2x e to the x dx. Add 4 here, 4 integral e to the x sine 2x dx. I changed the order, but that doesn't matter. So when you add them on the left here, you're going to get 5 integral, right? 4 plus 1. E to the x sine 2x dx equals e to the x sine 2x minus 2 e to the x cosine 2x. All right. Now what do you do to finish? just divide by 5. And we're going to get integral e to the x sine 2x dx equals, this is all over 5. You can just leave it that way, but I'll do 1/5 e to the x sine 2x minus 2/5 e to the x cosine 2x, and then plus a c. Okay, and that's the solve for the integral with algebra type. So this is the quicker version of it, right? That works sometimes. And the previous example was a much more complicated version. And the reason the previous one was more complicated is because we actually had to do the integration by parts twice the long way rather than with tabular, right? The table really makes integration by parts twice easy compared to not doing tabular. All right. What happened? All right. So I haven't seen any definite integrals with integration by parts. So if I don't see one in like the next 20 seconds, I'm just going to make one up. But we'll see. Okay, make one up. I'm not seeing it. Maybe you don't even have to do any. I don't know. Let's do a problem. Make one up. So I'm going to combine this with something from the previous section. So let's do integral of 5x squared sine 9x dx, and I'm going to do this from 0 to pi. Okay, so it's a definite integral, right? Now, this is integration by parts. It's not the kind that we just did, okay? Because the reason we had to do this roundabout way to find the integral here was because no matter how many derivatives you take over here on the left, you're never gonna get you're never gonna get to 0. And no matter how many antiderivatives you take, you're never gonna get to 0, right? So the integral never simplifies with exponentials and signs. But this is different because 5x squared, you take a couple derivatives and it's gone. Okay, so this is an ideal candidate for tabular integration. So we should do tabular integration by parts. So let's make the table. Well, yes, over here. I don't know why so much room. You don't need that much room. All right, u dv. And I'm ignoring those limits of integration. We ignore them till the end. So pick your u that way, and then pick your dv. Oh man, 9x. Okay, it is what it is. So take some derivatives. The derivative of 5x squared is 10x. The derivative of 10x is 10. And the derivative of 10 is 0. Now, those are derivatives. In the other column, you're doing antiderivatives. So the antiderivative of sine 9x is negative cosine 9x over 9. The antiderivative of negative cosine 9x over 9 is negative sine 9x over 9, but combined with the 9 that's already there, so over 81. And then the antiderivative of negative sine 9x is going to be positive cosine 9x over 9. And you need to know what 9 times 81 is, which I don't. That's impossible to know. Nobody knows that. So I'm going to get a calculator rather than think. 729. There it is. Okay, so there's my table for tabular integration. Now, what are we going to do with it? Well, what we did before, right? So do that with a plus, that with a minus, that with a plus, that with a minus. And since we went to 0, that's helpful. We'll see why momentarily. So give myself as much room as possible. Work it out. So we multiply the first two things, right? We got these two, just alternating colors here, that's all. Then these two, and then these two. Okay, so green ones. So what do we have? We have negative 5x squared over 9 cosine 9x. Then we got the next one, so we did that. Now let's do that. Looks like we got a negative, so it'll be a positive 10x over 81 sine 9x. Then we got to do these two. Looks like plus, which is plus. So plus 10 over 729 cosine 9x over, I already did that. So just cosine 9x. All right. Now the last one, remember the last one's an integral, but in this case it would have been the integral of 0 cosine 9x over 729, but this is 0. Okay, so when you integrate 0, you get 0. So if you end up with a 0 here, then you don't need to add the last one on the list because it's 0. Okay, so that's my integral, but I'm going from 0 to pi. So this is going to be awkward. We're not going to get a final answer, but you put in a pi everywhere. So negative 5 pi squared over 9 cosine 9 pi plus 10 pi 81 over 81 sine 9 pi plus 10 over 729 cosine 9 pi minus, put in a 0 everywhere, so 5 0 squared over 9. Back that up a little bit. When you put a 0 in to an x, it's going to be 0, right? So this whole term is going to be 0. And when you put a 0 in here, because there's an x, it's going to be 0. And the third one is not, because there's no x in the part outside of the cosine, so it's going to be like that. Okay, so that's what we get. Now, just useful facts here, right? What is sine of any kind of pi is 0, but cosine of pi or negative pi or anything like that, an odd number of pi basically is -1. So that'll help me evaluate this. So what I'm going to get, box, this cosine of 9 pi is going to be -1. So -1 times what's already there is going to give you 5 pi squared over 9 plus the sine of 9 pi is 0, so I'm not going to write that. But then you've got the cosine of 9 pi there. Cosine 9 pi is -1 again, so we get negative 10 over 729. And then on the last row we got minus cosine 0. Cosine 0 is 1, so this is minus 10 over 729. Which looks like now, if I did this right, I could have made a typo here or something. Negative 10 over 729 minus 10 over 729 is negative 20 over 729. So that's it. Now the point here was not to, get an answer, The point was just to show you what to do really with the limits of integration, which is do the entire integral first, which we did, and then plug in the pi and plug in the 0 like normal. Okay? Okay. So you do have to do this tabular integration a little bit on this this assignment. All right, I think that's it. So we are done for right now. See you next time.